Hello and welcome back to part 2 of section 2.1 of geometry. Let's now complete the example problems together. For example 1, we need to write a conjecture that describes the pattern in each sequence. Then use your conjecture to find the next item in the sequence. First up, we have some movie show times. First one is at 8:30 a.m. I don't know of any theaters around me that start that early, but okay. Then the next one is at 9:45 a.m. So from one to the other, 8:30 to 9:30, that's plus 1 hour. And 30 to 45, that's an hour and 15 minutes. Then the third one is at 11. So from 9:45 to 11, 15 minutes makes it 10 o'clock, another hour and 15 minutes there, which is the same. And then let's see, 11 plus 1 hour makes 12, plus 15 minutes makes 12:15. That's perfect. Okay, so it's plus an hour and 15 minutes every time. So if we were to continue that, 12:15 plus an hour 15 makes for 13:30, also known as 1:30 p.m. So that's the next. I still didn't really write a conjecture here. Describes the pattern each sequence. So let's write a quick sentence here. Now let's see. The next movie will play. We're not talking about the last one that we found the next item. We're talking about the general pattern. Every time the next movie will play 1 hour, 15 minutes after the previous. I should have given myself a little more space there. That's okay. I think I can move this piece. It takes the writing with it. Never mind. On to section B. We've got a square here made out of segments. And then onto that square we have drawn some additional segments. It took 4 segments to make the square, of course. You can think of this as a classic toothpick or matchstick puzzle. And then it took 1, 2, 3, 4, 5, 6 more for a total of 10. Okay, so from 4 to 10 we added 6 of them. And then we added 8 more for now a total of 18. And then we added 10 more for a total of 28. So that's not consistent, but notice the numbers added are growing consistently. So 2 more there, 2 more there. Let's check what would it take if I added 2 more here. That means I would gain 12 from 28 to 40. 28, 30, 40. Yes, that is indeed the case. 28 plus 12 is 40. So we will just continue on our way. Add 2 more than that. So that's plus a 14. 40 plus 14 would be 54. So what is the general rule? Each figure increases by a number 2 more then the last number increased. Okay, example number 2. Algebraic and geometric conjectures. So now we're going to make a conjecture about each value or geometric relationship. We will have to list or draw some examples to support your conjecture. A says the sum of 2 odd numbers is what? What about the sum of 2 odd numbers? I don't know. Let's find out. Pick an odd number. 1 plus 3 is 4. 3 plus 5 is 8. I don't know. 13 plus 1. Those are 2 odd numbers. I can repeat some. Sure, why not? Is 14. 5 plus 5. What if it's the same number? 5 plus 5 is 10. Okay, what do these have in common? 4, 8, 14, 10. They're all even numbers. Does that make sense? Sum of 2 odd numbers is always an even number? That's what I'm going with. The sum of 2 odd numbers is always an even number. Oh, you know what we didn't check? We didn't check. What about negatives? Like negative 3 plus 5. No, that's still 2. Okay, that checks out. All right. How about segments joining opposite vertices of a rectangle? I'm going to be a little tricky here. Luckily, Notability does let me draw instant perfect rectangles. Segments joining opposite, let's make those a dashed line. Why not? Here to here, and from here to here. Okay. Well, I need more examples. So let's get a long. I'm still dotted lines. Let's get a long, skinny rectangle like that. Joining opposite vertices. Okay, what do you see about those? How about length? They look pretty symmetrical to me. Maybe we can measure these. I know I'm not starting at 0. That's okay. From 1 to, it looks like 1 and a, what is that, a fourth? 1 and a fourth? Should I start at 0? Oh no, the middle is 0. Oh, I'm sorry, I'm reading this all wrong. Okay, let's start at 0. Here's the 0 point. Here we go, and I bet I can scale this down. Just let me. Oh, but I can move the increments there. See how much it is. I can mark and remember. So this one goes to the exact same place. Okay. How about over here? This one there. Put that one on 0. Tilt up. A little more. Goes to there. And the other one is, yeah, that's the same length. Okay, makes sense to me. So that's my conjecture. Back to solid line, please. Segments joining opposite vertices of a rectangle. The segments have the same length, or you could just say are congruent. Good. We'll prove whether that's the case or not sometime later when we get to studying the rectangles. Now, example number 3 is quite involved here if you are copying this into your notebook. So follow along with the process. You do not need to write all of this following. But let's at least read together. The owner of a hair salon collected data on the number of customers her salon had each Friday, Saturday, and Sunday for 6 months to decide whether she should increase the number of stylists working each weekend. The data she collected are shown below. Okay, I don't know how she's going to make that. Is there some minimum she's looking for? Let's see. Month 1, we had 200, 600, 500, 200, 600, 600, 366, 47. Oh, we could look at the total. 1,300, 1,500, 1,600, 1,800. These are all going up. Well, okay, not quite going up, but month 6 is definitely more than month 1. But if we really wanted to see this, the best bet would be in a graph. I, of course, have copied the graph directly from the book there. And this is what I would like to focus on because I think we can very much see, especially on the total, make a conjecture based on the data, explain how this conjecture is supported by your graph. Well, these numbers are going up. Drawing a line of, it's probably not the best fit, but a fit line through those totals. The number of customers is increasing. So the conjecture would be, as far as should they increase the number of stylists, then yes. What's her name? The owner of the salon. So my conjecture is the owner should hire more stylists for the weekend. Why? The data shows a trend. My conjecture, right? It might not continue this, but it shows a trend. Increasing number of customers. At some point, they will reach a breaking point there where they don't have enough people. And that might have happened already. Notice the very last one has already leveled off, as it were. So it might be because they were full now. They can't accept any more customers to that. All right, and then finally, finding counterexamples. Let's try this. Find a counterexample to show that each conjecture is false. This is going to be, sometimes they will be very obvious. Sometimes it will take a lot of testing and checking things. Sometimes it will require some more out-of-the-box thinking, like, oh, well, what about this? What if this other situation? So let's take a look here. If n is a real number, then n squared is greater than n. Well, let's try some regular examples. If n equals 2, 2 is a real number. 2 squared equals 4, which is greater than the original number 2. Yes, that holds. So you might think, oh yeah, squaring a number always makes it bigger. What about, but it just said real numbers, other numbers. What about if n equals -1? Aha, negative. Actually, hold on. That's not what I want to test right now. -2. You'll see why in a moment. I just had another idea. Negative 2 squared is also 4, which is greater than negative 2. So the negative part actually doesn't change this. But what about 1? If n equals 1, 1 squared is just 1. And that's not greater than 1. It's equal to 1. So we don't gain anything if n equals 1. So there's our counterexample. Boom, done. I thought we'd have to get into like fractions or something fancy. Well, that would work too, actually. Anyways, B, geometry 1. If JK, well, let's start drawing a picture here. Here's J, here's K, is equal to KL. So we have another distance from K to L. Pretend those are, you know what, we don't have to pretend. I will mark them. This is congruent to that, guaranteed. Then K is the midpoint of segment JL. That certainly seems to be the case with how I've drawn it, but nothing says that these have to be in a straight line. There's JK, here's KL, right? It didn't start with straight line. This is what I mean by the out of the box. Oh, well, they didn't specify. They didn't give me this constraint. Let's do something more creative here. Then segment JL is over here forming a triangle. K cannot be a midpoint because it's not collinear. So this is the entire counterexample. That whole diagram, boom. You could explain here. K is not a midpoint if it is not collinear. All right, and that is the last example that completes the example problems for section 2.1. So long, farewell, enjoy the rest of your day.